I don't want to give you a pathological training. I just want to give you a brief explanation of why this is important. And this is the reason. We have this kind of classification between different adenomas. So for the endoscopist, when he sees a lesion in the colon, usually he calls it colorectal polyp. For us, we have to give a more specific diagnosis. And the main two groups are this one, conventional adenomas and serrated polyps. And then we will focus now, and we also focus it for our task on conventional adenomas because they are quite challenging. But if we would like to focus also on serrated lesions, it will get very, very more challenging. So at least initially we wanted to focus on this setting. And as you can see, we have some morphological features which make us say if an adenoma has some kind of low-grade dysplasia or high-grade dysplasia. And this is quite a road which goes from normal tissue to low-grade dysplasia, high-grade dysplasia, and then invasive carcinoma. So it's important to distinguish between these different kind of lesions. And then we have also stratification based on the architecture of these lesions between tubular, tubulovillous, and villous adenomas. So we also selected these settings because this kind of diagnosis is just based on morphological features. So it's a task which could be effectively tackled by image analysis and deep learning analysis. This is an example of the challenge. This is the challenge for the pathologist, so it will be the challenge for the tool we are going to develop. Here on the top left, you see some kind of normal glands in the colon. Here on the bottom right, in this half of tissue, you see a low-grade dysplasia. What does it changes? What does it change? It changes the kind of nuclei. You can see here on the basal layer, you see these nuclei which are more evident, more dark compared to this kind of small round nuclei. And in this case, I would say that there are no other major difference. Probably if we would have another kind of image, you will see also some other characteristics. But anyway, this is the kind of the problem. And then you cannot say just presence of dysplasia. You have to stratify it to be effective in your diagnosis and also to be effective, to give an effective tool to the pathologist. And this is the example of the stratification of dysplasia. Here you see a low grade, here you see a high grade. So you see in this kind of, for this kind of problem, we focus on a quite high magnification of the image because you have to recognize this nuclei, you have to recognize how atypical they are to distinguish between this situation and this situation. But it is not sufficient for your diagnosis. As I told a few seconds ago, you also to give an assessment to the architecture to distinguish between tubular adenomas and villous adenomas. And what is the difference between these two diagnoses? The difference is here in an image. You can see this difference in an image with a significant lower magnification. You see here, it has a very lower magnification because you have to see this kind of architecture. Here you have a tubular adenoma, and here you have a villous adenomas, and the villous adenomas is characterized by this kind of finger-like protrusions of the adenoma. So it will be very difficult to distinguish this from this one if, for example, you would focus on this kind of high magnification images where you see like just a small square of tissue. You have to get a broader view. And as we will be discussed in the second part of the presentation, this is one of the solutions we identified after, as told previously, Marco, by discussing, because it's not so immediate to transmit some concepts which for us are very, very simple, straightforward, but maybe we do not consider that for developing a deep learning analysis tool, it makes a complete difference if it has to approach the image this kind of high power magnification or low power magnification. And sometimes the information you get from the analysis, it's not sufficient at one single magnification. So this is just to get you a background on which kind of images we have analyzed. Which is the relevance? Here you see an example of one very recent guideline. This is the European guideline. So it should be used in every center in Europe, theoretically. And as you can see here, if we wonder, but it's important, the answer is yes, because a polyp in which we make a diagnosis of high-grade dysplasia goes into a different follow-up because it's defined as a polyp recurring surveillance. So it will be more exams, more colonoscopies during the next year, the following years. So this is just one example of how the morphological features have a direct impact on the patient. And regarding the general topic of deep learning analysis for colorectal cancer, I just bring here some examples on other tools which I've developed. In these cases, they are used by the endoscopist, because here you can see the image from the colonoscopy endoscopic examination, and here you can see how macroscopically a polyp appears. It's very small in most cases, and it's not so difficult. It's not so easy for the endoscopist to identify these kind of lesions. You have to consider that an endoscopy lasts just 15 minutes, and you have to see practically meters of tissue. So this is a first example. And then moving to the histopathological analysis, I will just conclude with some background data, which we evaluated before starting with our project to understand which was the state of the art. And as you can see here, some attempts were made to approach this task through deep learning, but there were some missing aspects. The first one was, for example, the comparison between high-grade and low-grade dysplasia. For example, here you can see that they compare the different architectures, tubular, tubulovillous, in this case also some kind of other serrated lesions. But for this tool, they have not considered the grade of dysplasia. So, for example, this was an important limitation because the tool would not be able to replicate the pathological diagnosis. This is a more recent example. As you can see here, they started from about 500 slides, and this gives us an idea. This was published in JAMA Open, which is an important journal. This gives an idea of how it's difficult to get big data in this setting. If we will probably imagine from your point of view, what do you mean with big data? You would probably imagine some thousands of cases. But as you can see here, many times you have to start with very, very lower data sets. And in this case, in this recent paper, as you can see, it was surely an interesting analysis, but there were again some kind of issues. For example, again, the lack of dysplasia grading, because it's not so easy to approach this task. And also the lack of analysis of normal tissue, which is quite important because you get normal tissue sometimes and you have to recognize it. And also some kind of lower performance during external testing, which is one of the greatest and most common problems in this setting. When you try to replicate your analysis of a completely different images, you will get some poor results for many different problems, but it will take so much time to discuss. So in conclusion, I will just report an example of some the kind of more recent papers about this topic. This was published in Lancet Oncology, which again is one of the most important journals considering the oncological research setting. And in this case, deep learning was applied to predict the presence of microsatellite instability, which is a molecular feature. And this kind of features are becoming absolutely critical for treating the patients. But this kind of analysis sometimes are quite expensive. So in this case, the authors also proposed this kind of approach, because if you get an effective tool with good sensitivity and specificity to predict this kind of molecular features, they could be very relevant, for example, for some countries with lower budgets for healthcare, because maybe in our situation, we will not accept anything less than 100% sensitivity and specificity. No? When you do a molecular test, our requirement is to get it right. But maybe in a setting with lower resources, this kind of tools could be extremely important. And also from a biological point of view, it's very fascinating that by using some maybe not so evident morphological features, in this case, the presence of a mucinous component, and other characteristics that the pathologist will not be able to recognize. But by using this kind of approaches, you can get an estimation of the hidden molecular profile. So this is where the research is going, and I think it's very, very interesting for the next few years. Now I will give the floor to Carlo, which instead will discuss about what we got with our within our use case with our analysis. Thank you. I stop sharing.
Thank you, Luca. Now you got an idea of the interaction with the pathologist. So we are simulating the case you just visit the doctor, and now you need to solve one problem with deep learning, in particular with the library that we are developing in this project. So Carlo is the data scientist that will play the role. Okay, Carlo, the floor is yours.
Okay. Hello, everyone. My name is Carlo. Wait, because I can't. Yes. So can everybody hear me? Yes. Nice. So my name is Carlo. I'm a PhD student at the University of Turin in Italy, and I will now present you what has been our proposed deep learning based approach for tackling this issue. So as we already said, first of all, thanks Luca for your presentation and for your introduction. So our efforts have obviously started by collecting data sets. And this was an enormous effort by the pathologists. In total, we have collected around 450 all slides images, and as you can see in the table reported. But it was not enough, because as you can imagine, in a single image, there may be different types of tissues. So for example, we could always have probably some normal tissue. And so it's not enough to just use the entire image, even if it was possible. And so there was a need also to collect some more specific annotations for the specific region that we had to look at in each image. And so this required much more manual effort by the pathologists. So in total, the area we collected is around 200 centimeters squared. So as you can imagine, given that these are microscopic images, it's a lot. And so this just to show you that it is one of the most important steps when doing any kind of, let's say, medical deep learning based work, and that is to collect the data sets. So the dataset we collected is been categorized in 6 different classes, and which are the among the ones that Luca has showed you earlier, which are normal tissue, hyperplastic polyp for the serrated classes, and then we have tubular and tubulovillus polyps. And then we also have the annotation about the dysplasia grade, which is low grade or high grade, and this is for tubulus or tubulovillus. And so what we try to do at first is obviously we try to perform let's say a baseline benchmark for this task. The first challenge is how we can process these kind of images. So as we have already said, these images are very different from let's say natural images, and also from other kind of medical images, such as chest X-rays and so on and so forth, because they are usually very large. One all slide image can reach up to, let's say, 100,000 pixels by 100,000 pixels. So you can imagine that it's not so straightforward to process it entirely with a neural network. And so the most common approach, which is the one we follow, is to crop the entire image into multiple patches, usually squared patches, with a different size. And after we extracted these different patches, then we feed the patches to a neural network, and then we obtain our predictions. And of course, before feeding the images as input to the network, we can apply different kinds of pre-processing. So for example, we can focus on normalizing the color. There are many techniques which are proposed in the literature, and one of the most commonly used technique is the one proposed by Machenko. These kind of images in histopathological images are usually colored with chemical reagents, which are hematocillin and eosin, if I remember correctly, H and E. And of course, given that they are chemical reagents, their composition might vary from laboratory to laboratory or even within the same laboratory. And so it might be useful to try and normalize the different, let's say, contribution of each of the reagents. Or for example, we could try and also convert the images to grayscale, because maybe for a neural network, the color information is not so useful in certain settings. And that's exactly what we, first of all, we analyzed. So we compared different pre-processing techniques, and we found that in our case, there wasn't so much difference among them. And surprisingly, the best results were achieved in this case using the grayscale conversion. Of course, as I mentioned, when we extract the patches from the all slide images, we have to choose the size of the patches. And in order to find a suitable size, we performed an analysis of different sizes, and ranging in this example from patches with a square with a side of 300 micron to 1000 micron. And we analyzed the different performance across all of the sizes for the different classes in our datasets. And this gave the first hint that this problem should be tackled at different sizes. So there is no one size fits it all in this case, because as Luca was showing you earlier, there are different features which must be looked at different sizes. And in this case, the results we got were okay for a baseline, of course, study, but they weren't enough for a clinical application. You see in this table, they are reported in more details. So we can achieve, let's say, reasonable performances in most of the times in detecting the hyperplastic polyp, but that's the, let's say, the easiest task even for pathologists. It's not very clinically relevant. What's more interesting is predicting the correct grade of dysplasia, which is high grade or low grade. And also, as Luca was saying, distinguishing in tubular versus tubular villus or villus polyps. And so these were obviously the cases in which our results were lower. And so what we have then tried to do is to try and collect all the knowledge that the pathologists shared with us. And in order to try and build a complete end-to-end pipeline for diagnosing both the polyp type and both the dysplasia grade. And so to do that, we built what we call a multi-resolution ensemble, because we have different models and each one of them has the task of predicting and classifying different classes and features. So in the first of all, we start from the easiest task, which is predicting or classifying hyperplastic polyps. And this can be done at various sizes. So we chose the 800 micrometer square patches because it's a reasonable balance between image size and features in the image. Once we determine that an image is not an hyperplastic polyp, we then look for tubulovillus or tubular adenomas. And as Luca was showing you before, this has to be done at larger sizes. So to do that, we extract patches at 7,000 micron. So this can give us a great overview of the macro structure in the image. Of course, 700 micron at the physical resolution of the all slides could be could be a huge image. And so, but in this case, given that we are interested in only finding the macro structure in the image, we can perform a subsampling operation in the pixel resolution, okay? And after we determine that the image is either a tubular or a tubulovillus polyp adenoma, then we can try and predict the grade, the dysplasia grade. And this, on the other hand, has to be done at full resolution of the image, because we are interested in looking at smaller and finer features such as cells nuclei. So in order to look for mitosis and stuff like that. And for this task, so we employed again 800 micron patches, which gave strikes the, let's say, the best compromise between size and results. So once we combine all of these models into an end-to-end pipeline, we are able to significantly improve the detection performance, let's say the classification accuracy. So you see in the figures that on the left, we have a baseline model, which only works at one fixed size for the patches. And on the right hand, we have the multi-resolution ensemble. So the improvement is very well noticeable. Well, then, of course, there are still some limitation in these works. But even though we were able to include both the dysplasia grade and both the adenoma type, and also having a normal class, for example, there are not all of the polyps classes are included. Let's say some of the serrated adenomas are missing. And of course, if we can collect more data, that's always a better thing. And also we would be also interested in validating our models externally. So for example, on an external data sets. But as Luca has showed you before, that's not so easy to do because not all of the, let's say, publicly available data sets have all of the information that we actually need to perform our inference. So these are the main challenges that we had to encounter. And these are the main challenges that in the medical processing, image processing field are very common. So for example, most of the times when you collect data, you can have partial annotations. So that's what it's called weakly supervised training. So you might have a very large data set, but only some subset of it is strictly annotated. And then there is also the challenge to scaling up your pipeline and your models to very large images, such in this case, and collecting more data as well. We can try and tackle the, let's say, the data scarcity issue, maybe by thinking about some smarter augmentation technique. So the usual augmentation techniques, such as affine transformation and stuff, we can maybe try and synthesize new images using a GAN-based approach. In this example, we are working on a conditional GAN-based pipeline to synthesize new tissue patches. And so the aim of this work will be to further increase the accuracy of our model, especially for dysplasia grading, which is the most important task of it all. And that's what something we are working on now actively. And as Marco has said in the beginning, obviously there's always the issue of explainability in neural networks, especially in the medical field. And and it's always a loop of keeping of interacting with the pathologist and so on.
If there are no live questions, we move to the next use case that is about lung nodule segmentation. So it is, in this case, it is easier to tell the difference between the doctor and the data scientist. Before was much more difficult. So Marco and Daniele, present yourself and start as soon as you want.
Okay, thank you. Good morning to everybody. I'm Marco Grosso from Institute of Radiology of Department, Radiology Department of City of Science and Health of Turin and University of Turin. I just say a few words about the clinical topics to introduce the real, very real stars of DeepHealth computer scientists. A brief history of our hospital. DeepHealth took place in my hospital, and the City of Health Science of Turin is the oldest hospital in Piedmont, and one of the largest in Italy. It is regional and national reference center for many diseases, particularly for organ transplant. 300 years of healthcare for city healthcare. In Molinette, my hospital south, where it was rebuilt in 1935 in the site that we still occupy today. Radiology department of my hospital is a great medical unit with about 100 radiologists, 114 radiographers. Excuse me, I lost my presentation. Okay. It includes the radiological service of Molinette Hospital, which this is the general hospital, Regina Margherita Hospital, pediatric service, Sant'Anna Hospital, gynecological, and City Hospital, this is the trauma center. They have many teacher research in different sites, imaging, public health, social science, clinical governance, statistics, information communication technology assessment, and health impact assessment. Department has 14 computer tomographies, 8 magnetic resonance, and 1 PET CT, 5 angiographic interventional rooms, and 1 radiology unit. In addition, of course, to a wider range of radiological ultrasound rooms. It's a great research structure with more than 100 young physicians and radiographers in training. It performs about many imaging examination a year. Radiology 2, my division is a site of department where the experimentation was mainly carried out. When I say the heroes of our experimentation are the pulmonary nodules. A brief representation of CT scan. CT scan is a procedure that uses a computer linked an X-ray machine to make a series of pictures of RS inside the body. The pictures are taken from different angles and are used to create three-dimensional views of tissues and organs. Sometimes to increase the chance of seeing disease, a drug called contrast medium is used, which is injected into the venous circulation to make the blood vessel opaque and reveal eventually neoplastic lesion. Pulmonary nodes has very small focal radiographic opacities that may be solitary or multiple. A very classic solitary pulmonary nodule, SPN, is the single spherical, well-circumscribed radiography opacity measuring less than or equal to 30 millimeters in diameter and is surrounded completely by aerated lung. SPN is a coined term that in the past described solitary nodes detected incidentally by chest radiography, And today, most nodules are detected by computer tomography. The detailed CT images frequently identify more than one nodule or a larger lymph nodes. Indeterminate nodes are those that do not possess features clearly associated with a benign etiology, such as benign pattern of calcification or stability on imaging for 2 years. On CT scan, a nodule appears as a rounded or irregular opacity, well or poorly defined, measuring up to 3 centimeters. Technological advances in chest imaging and increased the use of CT as a diagnostic modality have led to incidental identification many small pulmonary nodules. You see in the picture on your right. The majority of these are benign. The actual risk for malignancy in sub-centimeter nodules is lower than the predicted risk based on the clinical radiographic criteria for pulmonary nodes. Mayo Clinic, the great expert, best expert in radiology, in chest radiology in the world, CT screening trial reports 0% of nodules measuring under 4 millimeters, and 0 and 8% measuring between 4 and 7 millimeters in diameter are malignant. Another study reports 0% of nodules measuring 5 millimeters in diameter are malignant, while the rate is 5 and 9% for those measuring 5 to 9 millimeters in diameter. As you can see in the table, the probability of malignancy of the nodule increases with size. A nodule of 3 centimeters, very high probability of being malignant. The prevalence of pulmonary nodes change significantly across the studies. This variation stems from the inconsistency among studies emitted and rather population and reporting results. Most lung nodules are detected incidentally when I say of CXR, chest radiography, or CT scan obtained for other purpose. It is estimated that few CXR scans will incidentally detect pulmonary nodes. In CT angiograms obtained to diagnose pulmonary embolism, which is a pathology important for emergency department any day of our life. A study reports 13% of cases to have incidental findings of pulmonary nodes. Our task, or Dr. task in this experimentation was to identify in our large archive of images the cases that could be in interest to the computer scientists. We hope we have been good. Thank you. Riccardo, it's for you.
We cannot hear you, Riccardo.
Can you hear me now?
Yeah.
Okay. So I'll just share the presentation. Okay, can you see it?
Yes, we can see it.
Okay. So as Marco Grosso mentioned before, here we are talking about nodule segmentation in CT scans. And so these nodules are small focal lesions. They can range from 5 to 30 millimeters. And there can be one or multiple nodules. So for example, here in this figure, you can see there are 5 nodules. So the goal of this system is to segment and detect lung nodules in CT scans, so that this can be a tool to improve the efficiency in medical diagnosis and help the radiologists to find these nodules. So typically we have in this figure, we have on the left the input and on the right the output. So this is a segmentation map where 0 is the background, so no nodule, and 1, the white pixels, are the nodules, so the tumor masses. Here, there's the pipeline of automatic annotated instrument for detecting lung nodules. And so the input is the CT scans. And then there is a pre-processing functions. So for example, we convert the pixel into Hounsfield units, then we apply windowing or rescaling and so on. So we have some pre-processing techniques. Then the input already pre-processed by this function, is the input for the deep learning model. That can be, for example, a UNet model. And then we can do the task that we want. So for example, image classification, semantic segmentation, object detection, and so on. In our case, we want to do semantic segmentation. So we want to label each pixel with 1 or 0, background or tumor. So as Marco mentioned before, this is an example of how to the inputs are made. So we use the CT scan, and so typically the CT scan uses X-rays to generate and so the rays pass through the tissues, and typically the more dense is the tissue, the more X-rays absorb it. So in this example, we have a spiral CT scan. So we have a single source and multiple detectors, and this detector rotates around the patient and produce the CT scans. So the CT scans are saved using the DICOM format, which stands for Digital Imaging and Communication in Medicine. And it's a standard which defines the criteria for communication, visualization, and storage of biomedical information. So that in this way, the transfer medical scan between different hospitals, for example, is easier. So a typical DICOM file has as you can see in this figure, has a header part and the dataset part. And in the metadata information, we have many attributes. And so for example, the main ones that we use in our pipeline are, for example, pixel data, pixel array, where the image is stored, the window width and the window center, pixel spacing, and so on, that I'll explain later. So as we saw in the pipeline, the first step is Hounsfield units. So we have these raw pixel values in the pixel array attribute of the DICOM file. And we want to convert these raw values to a unitless physical quantity, which is called Hounsfield unit. So we use this unit to describe the radio density. So for example, here we can see that different ranges of Hounsfield units correspond to, I don't know, for example, bone or muscle or air or other gray matter and so on. So the Hounsfield unit scale is a linear transformation of the original linear attenuation coefficient measurement, in which the radio density of distilled water at standard pressure and temperature, called STP, is defined as the 0 Hounsfield unit, while the radio density of air at the SPT is defined as minus 1000 Hounsfield units. So to convert raw pixel to Hounsfield unit, we just apply a linear transformation, where the X is the store pixel value, M is the value of the rescale SOP, B is the value of the rescale intercept, and Y is the rescale value, the output, so the Hounsfield unit. And so what is windowing? We want to see different tissue or part of the CT scan based on the windowing operation. So we have these two attributes, window center and window width, that represent the brightness or the contrast of the DICOM file. And we can see that, for example, if we increase the window center, we can see some bones on the upper right figure. And we can see also that we can change the window width, and so the contrast will change accordingly. So the question is, which windowing setting do we need to use for pre-process our input and feed this input to the neural network model? It depends obviously on what you want to see. So for example, there is the lungs range, the mediastinum range, or the bones range. In our case, we want to segment lung nodules. So this windowing operation, we set the window width and window level with minus 600 and plus 1600. So when we pre-process the input, we know some units, converting raw pixel in alpha units, and we apply windowing on them. We can feed the inputs to a neural network model. So in this case, we can see a typical UNet model, which is one of the most employed network for biomedical image segmentation. And so in this example, we can see that UNet has an encoder and a decoder part. So we use our input to decrease its size to map into an embedding, a low-dimensional embedding. And from this embedding, we update and we produce the output segmentation map. So this is one of the typical way to do image segmentation. So we have the input and we want to produce the output, where in this case, the output is a binary mask where 0 stands for background and 1 stands for the white pixel. So this is what was overview of the first part of the pipeline for image segmentation, for lung nodule segmentation. And now Daniele will talk about a new dataset called UnitoChess. So Daniele, the floor is yours.
Thank you very much. I take the screen. Share. Can you see the slides? I think yes. So thank you, Riccardo. I'm Daniele Perlo from Città della Salute. I want to briefly introduce the data set that we have collected thanks to the DeepHealth for this use case. We call it UnitoCast, and it will be soon released and public. Behind this vintage logo made of CT scans, there is our relation of CT scans and pulmonary nodules segmentation maps. As a short introduction for UnitoCast, let's see the comparison between two of the largest datasets already public and available for segmentation pulmonary nodes, LIDC and Luna. UnitoCast shows the highest number of annotated scans in DICOM format compared to both datasets with more than 3,000 images. That is more than the sum of the other two. And each one is followed by its own segmentation map in PNG format. UnitoCast is not only has the largest number of annotated nodules, over 10,000, but also with a higher variety of the nodule sizes. In this slide, we can see how the dimension of the nodule are distributed within the dataset. Most of these fall between 10 and 30 millimeters in diameter, which is the size of the most frequently pulmonary nodules. The dataset is already divided into 3 splits: training, validation, and test, in order to make the comparison of different algorithms and studies more and more practical. As the subsets have been created in such a way that all the scans for a single patient belong to only one and the same split. Most important, the dataset is composed by images from a very large variety of CT scanning machines, as shown in the graph. Most medical data sets have a single source as image acquisition system. Each acquisition system has its own characteristics that can introduce biases into the training neural models. In our case, the sources inhomogeneity helps to counteract this bias effect. Speaking about of neural network training, what metric we use in this use case? We use the dice loss defined as one minus the dice score. Practically, the dice score tells us how much the intersection between the generated segmentation area and the original one is extended with respect of the sum of the two. Minimizing the dice loss is therefore equivalent to maximizing the intersection between the two areas. About the evaluation of the model, the intersection over union score is commonly used for segmentation problems, especially also in the medical field. This matrix takes into account, as for the dice score, the area of intersection between the generated segmentation map and the ground truth. But we can see that also involves the ratio of in the ratio, the union of the two underlying areas. This ratio tells us how precisely the two maps actually overlap each other. An intersection over union equals to 1 indicates, in fact, a perfect matching of each pixel of the segmentation map with the ground truth. In this slide, we summarize the results that we obtain from our 2D UNet model presented by Ricardo in two different ways. The first one is a training from scratch using unit-to-test dataset only, while in the second one, there is a pre-training phase that is made by using the LIDC dataset, and then the network is trained on unit-to-test. The pre-training allows us to start from a configuration of the network in which the weights are already helpful for the solution of our task. We can see how for the dice score, a value of over 0.7 is reached on the test set, while it reaches about 0.6 for intersection over union. 0.6 seems not very high, but we have to think that the annotations are not never pixel precise on the nodules. We can see the two metrics plotted for each configuration on the right for the whole training phase, about 100 epochs. We can see that we can reach higher performances in blue by doing the portrait. Otherwise, we can also evaluate the goodness of each map by evaluating for each pixel if it belongs to a background or to a node. If we look at the confusion matrix below, we can see that the 87% of the pixels of the node are correctly identified, and we have the 97% for the background pixels. At the end, I would like to show a very short demo in which we can send a CT scan to our model that is deployed on on HACCP4AI, and the server will return the annotation for our CT scan. So I have just a problem because the screen sharing is not having me okay to reach the demo. So this is a very simple demo in which we can upload one of our CT scan, for example, this one that have a very big nodule. Open. And then we can submit our image. And the server return the segmentation map for this big nodule here. And we can see that it can effectively retrieve the nodules, and it's not finding any other nodules inside the nodule. With this, I end my presentation. I can leave the word to Enzo Federico D'Agata for the next use case.
I will give you some idea on the outline of the problem. Basically, we are talking about acute ischemic strokes, a standard examination when a patient arrives in the hospital is the CT perfusion. It's a standard because it's readily available in many centers, it's fast, and can give important therapeutically indication. Basically, we can go to the next slide. Basically, we have an occlusion of a cerebral artery. You can see here, you can see my mouse, I don't know, the green arrow, you can see in the regular CT, the green arrow on A, figure A.
Okay.
Yeah,
Oh,
you can see here there is an occlusion. You can see that there is no signal in the cerebral artery, and corresponding to this situation that you can appreciate on the standard CT, you can see other correlate in many different clinical examination. On the right picture, you can see all the different correlates. And basically, this can obtain with MRI or with CT, but we focus on CT. And we have basically 3 areas, and the different dimension of this area is what is really important to decide the treatment for the doctor. So basically, there is a core area. The core area is where you have a big damage that is no more recoverable. The tissue is already dead. When you have a penumbra that is an intermediate situation, it can be in part recovered, and you have the oligemia, that is where you have a complete recovery of the tissue. So what is it, perfusion? Basically, we inject a bolus of iodine contrast, and we measure the wash-in, wash-out of this agent to assess the blood flow dynamics. In fact, we can get the dimension and the damage of the core and the penumbra area looking at this wash-in, wash-out. And basically, we use the time concentration curves for each voxel, and we try to deduce the damage of the cerebral tissue looking at this curves. What is the problem? The big problem is that there are a lot of physiologic noise, and the fact that we are not in a normal way, in a normal situation, but we are in a pathological way, introduce a lot of different kind of noise. And this noise can be as arterial delay, or can be dispersion of the contrast of collateral circle. All this kind of noise it's a problem, because when we use the convolutional method, that basically, we can go the next slide, we can basically try to remove all this kind of problem from our signal. Often in a medical and practical situation, we have a failure of the algorithm. Basically, we can extract the blood flow, the blood volume, the transit time of the blood, and the time to peak of the blood. All this information are extracted by the time curve of the bolus. But as I said, in pathological situation, this is a kind of normal example. The blood flow is the integral under the curve. The time to peak is the time to reach the maximum. The CBF is the maximum slope, so the differential during the first part of the curve, and the mean transit time is the mean time for wash out. In normal situation, it's very easy. You can basically extract from the curve all your parameters that correspond to physiological important medical information. But in the real situation, you have a lot of noise, you have a lot of problems that can basically give a completely wrong estimation of this result. So the main goal for us is to have a very strong, very robust algorithm that can be fast and reliable in real medical situation. And this deep learning methods, machine learning methods can be a really way to solve all this kind of problem in the medical routine. I think that now we can start with the methods that we implemented.
Thank you, Federico, for the nice introduction and the motivation behind this very important problem. But now I want to dig a little bit further into some implementative details. So how all of this information from the patient is actually collected, how can we practically manipulate this data, what are the state-of-the-art approaches and techniques to try to tackle such a problem, and more concretely, why deep learning is really good and reliable perspectively to try to solve this issue. From a very practical point of view, from a very practical point of view, what happens to the subject undergoing this examination? Since we need essentially a map of the blood flow, blood volume, time to peak, and mean transit time, which are the 4 reference measures to get to the identification of the ischemic core, penumbra, and so on, the areas which are of interest for intervene in order to save the life to the patient. We need to undergo a particular exam, which is the CT perfusion. What is it? From a very oversimplified point of view, it involves a very elevated number of scans of the brain, in this case in particular. I personally worked with some of this data, and we're talking order 80 acquisitions per different levels. And what does it mean? It means that at the same height for the brain, we're going to take 81 or even more snapshots on how the blood is flowing, which means, of course, 81 times the tax of normal radiation, which is, of course, problematic. It's a huge amount of radiations which the patient need to undergo. Why is this all necessary? Because we need to track how the agent diffuses in the brain, and how all the blood is going to be distributed through the brain. Why? Because all of the areas which do not receive enough blood are the areas affected by the ischemic stroke. Then, of course, it will be up to the doctor to identify which is the core and what's the penumbra. But still, we need to track all of how the blood is going to be distributed through the brain. And of course, we need all of these heights to be consistent. So we need, for the whole duration of the exam, which is typically in the order of minutes, 2 to 3 minutes in the average, even somewhere less, somewhere more, but that's the order. We do not need to allow the patient to move the head, because otherwise, of course, the time tracking, since it is going to be referenced to the same height, is going to be subject to big errors. And of course, there are some approaches, state of the art, to track it. So what are going to be the traditional algorithms which are used towards the generation of these maps? Well, first, there is a phase which is called registration. With the registration, is saying, from a very high level point of view, we're going to set up the brain, the pose of the head equal, constant through time, and there are some approaches to do it. in order all the acquisitions to be consistent to the same height. Then, of course, we need to generate the time intensity curves, which are those presented by Federico, and the so-called arterial input function, which are both necessary towards the algorithm which generates the maps that are very useful to identify the ischemic core and the penumbra regions. The convolution algorithms are state-of-the-art, and they're the traditional approaches for solution of these problems. Registration, as mentioned before, takes a reference image, it takes a target, and tries to apply some rigid transformation with some noise cleaning and some standard pre-processing techniques to the data in order to put it always in the same pose. This helps the traditional algorithms to undergo towards some robustness algorithm. If we expect to find the brain always in the same pose, we know where a given, for example, a given vessel is going to be, roughly. And we're going to get consistently more robust towards head movement by the patient, which are just physiological. And so registration is a typical practice for image processing, especially for this kind of task. Arterial input function, what is it? It is also known as a plasma input function, and it refers to the concentration of the tracer in blood plasma in an artery measured over time. Essentially, it spikes when the concentration of the tracer is at its peak. And it is used from the traditional algorithms to generate the perfusion maps. And it is state of the art. It is something mandatory towards the guidance of the deconvolution algorithms. And here it comes to the question, why do we want here to use a deep learning based approach to solve this kind of problem? There are many reasons, some of which have already been mentioned, like the possibility to build models robust to noise. It is shown in many contexts, including and especially in the medical context, which proves on the field that if properly trained, deep neural networks are much more resilient to noise with respect to hand-designed algorithms for feature extraction and to perform image processing. It's an automatic learning process, so we do not need to impose very strong priors on the preprocessing. Of course, image registration is still a good practice to use, to deploy, but image registration is not always going to be a perfect method, because it can do just rigid transformation, but there are many other sources of noise from which this approach can fail. And these sources of noise sometimes are unpredictable. And potentially, and this is the most interesting part of the study, potentially, we can reduce the sampling rate. And this is definitely the final goal of this entire study. But we're gonna see that in a little time. So what is going to be the architecture we want to deploy here? It's definitely a UNet-like approach. I mean, it is a state-of-the-art architecture for deep learning, so why not to use it? Of course, we need to really think a lot on the kind of data we're manipulating here, and we need to really think on what kind of feature we're working on with. So, of course, we need to introduce some changes to this architecture to make it perfectly suitable for the task. For example, since here we're not dealing with the segmentation task, very strongly nonlinear pooling layers are not a good choice here, and we want, for example, to use average pooling layers, or strong nonlinearities like ReLU here might be a good choice, but actually we can slightly improve the performance, and we've seen this later with other kind of nonlinearities in which we allow, for example, some negative regions. For example, here you can use leaky relu and other small changes to this architecture to make it working well with this task. So the overall pipeline changes dramatically. We remove all of the arterial input function extraction and the by hand design of the convolution algorithm, and we just feed these images straight to the deep model. And yes, we have achieved some preliminary results in which, for example, here in the top images are the outputs map for the convolutional neural networks. In the lower part, we have the output of the ground truth, which for us is the traditional algorithm. Qualitatively speaking, the results are very similar to each other. And yeah, this is just to give you an idea on the generation for 3 out of 4 different maps. In this case, we've chosen blood volume, blood flow, time to peak. Why not all the 4 of them? Well, because 3 out of 4 are sufficient just to get all of the measures. So just showing even the 4th, the missing map, which is mean transit time, would be just redundant. Because just getting 3 of these mapping out of 4 is sufficient to get to the target results, to identify the ischemic core and the penumbra area. But this is just a qualitative point of view. We have done more. We have asked 2 doctors independently to segment the ischemic core and the penumbra area. And then, to avoid any source of bias, we asked a 3rd one to parse out the results. And here is the results we have achieved. Of course, here we present results in as volumes for both the ischemic correlation and the penumbra volumes for 12 different cases in the test, in a test set taken aside. And we see that there is the areas are very similar to each other. Furthermore, we wanted also to see what are the intersections of these areas. So we have evaluated also dice score results for this, for rater 1, rater 2, and the ratio. And we see a very high concordance between 2 independent raters, both on the CBV, which detects the volume, and CBF and TTP. And we see here that we can identify similar areas, similar regions, when using both convolutional neural networks and the traditional algorithms to identify ischemic area, ischemic cores and penumbra regions. But here comes the question. The question is, okay, we have achieved the same results having the same input, but we have just used the deep neural networks. What is the real advantage in using neural networks? Well, the real advantage is yet to be explored, is being explored actually, and here it is. We have ground truth having the 100% of the acquisitions, but now we can train the deep neural network subsampling the input, meaning that instead of having 80 different CT scans of our entire brain, we might need 8 with the, for example, for the 10%, or we might even need 4 with the 5%. This study is still at a qualitative point, but as you see, the generated output by the neural network having just a small fraction of the input of the acquisition here qualitatively is very similar, is very likely to the output which it would have having the 100% of the possible time acquisitions. So this is the next step we want to move through in the next future. And this would bring a lot of benefits from the point of view of the patient. Because why? Well, because the rate of radiations the patient is going to be subject to will be lowered by potentially the 95%, which will be very relevant, especially if you think that the poor subject has to undergo more than 80 CT scans in just 3 minutes. And the data was were a very big problem here. Why? Because since this topic is very specific, and since these data are very hard to retrieve, no data open source have been available. We have released the data set included 100 subjects with Zenodo. And we have released afterwards even a larger data set, especially thanks to the medical staff, Federico Dagat, Umberto Gava, and so on. All the medical staff, they took care of publishing this data and releasing it open source. What we did was just providing also with the whole packet the software necessary to reproduce the results, of course, using the DeepHealth toolkit. Well, this is it. Thank you very much. And I will give the stage back to Marco.
Okay, thank you. We're just on time to conclude this session. Just a quick recap and then lunchtime. I just want to go through this last bullet, trying to recap on the main lessons learned in this area. When we tackle medical problem, of course, the first obstacle that you have to jump on is the difficulty in communicating and using the same language between engineers, computer scientists, and medical staff. So the first lesson, spend as much time as needed to define and understand the challenge, understand the language, really understand the problem. I think this is quite simple thing, but you must devote the right amount of time to this. Then, if you will apply deep learning, you will have some particular problem. The first problem that you will face is to engineer the data collection phase. And for this phase, a common issue is that you don't consider all the possible sources of information in the very beginning. And it is very annoying to come back later, add information, reprocess some image, label again. So one other suggestion is to be as precise as possible in the definition of the data that you need, and therefore in the composition of the data set. The third bullet I want to stress is about pre-processing. Pre-processing is really important in the medical area for a number of reasons. Some are specific of the medical case. You have seen a lot about the need to co-register different images, different volume taken at different time. This is, of course, important. But in terms of learning, pre-processing can also be a prior that you put into the learning. And this becomes very important when you have very small data set. I mean, if you know that you are looking at the lungs, it may be useful to pre-process the image to segment the lung. But this is important, especially when you have a small data set. If you have a large data set, of course, the neural model can learn itself to do the job. So pre-processing is really an important thing. Also, in the radiologic example, you have seen that you have to convert the radiologic unit to images to input in your pipeline. This may be a trivial thing, but again, to be handled with care. Talking about data, another important point to increase the impact of all this study is coming up with a public data set. In all the use case that you have seen, we have tried to, we have 2 data sets that are already public and the third that is planned to be. And this is critical in the most of the time in the interaction that you have with the hospital ICT infrastructure and privacy issue and ethical issues. So of course, this can take time to address, so consider it before starting your study. Then, of course, don't forget that you are not working into silos. So deep learning applied to medical image is a constant learning thing. And don't forget to exchange knowledge between computer folks and doctors. And always take a lot of time to discuss the obtained results. The final 2 bullets are very important. Don't trust the results that you got in the first experiment. Try to understand and really explain the extracted feature and the decision you are making, because working in the medical area, explainability and trust is not an option. We are not telling dogs from cat, and this phase must be addressed as an important thing, of course. The last point that is very interesting, in my opinion, is the fact that deep learning from one side is a black box approach. So most of the time it will be tricky to explain what is doing, what is happening. But from time to time, this approach is also a chance to get some unexpected results that will challenge prior assumption, both from the deep learning theory or from the point of view of the knowledge that we have of some physical phenomena. In the area of medicine, of course, this tool is potentially an important tool to discover unexpected correlation, unexpected phenomena. And this will work only if you work in strict contact with doctors and not in your own silos.